I Hello, everyone. Welcome to the Graduate Student Community Seminar Series. Today, September 19th, we're hosting Dr. Junke Wang from Pacific Northwest National Lab. He got his PhD here at OU as a member of the Building Energy Efficiency Lab, and we're very excited to hear about his new work as a researcher at PNNL. Before that, though, I want to introduce the graduate student community and go over share some events and details that we have. So first, to introduce our community, our leadership team this year, myself and Rachel Bennett are the co-chairs of the GSC. Swapnil and Avinash run our publicity. Siavash is our treasurer. And we have support from a lot of dedicated team members, Mohammed, Luis, Roshan, Jason, Hamadri, and Naran. Professor Fro Chemistry is our faculty advisor. And past that, we want to invite everyone here to our weekly GSC leadership team meetings. This semester, we're hosting them at 4:30 on Thursdays. We're holding them in person again in the Dave and Susan Burt team room in the engineering lab building on campus. If you're interested in joining our leadership team or just attending the meetings and providing input, please reach out to myself or Rachel Bennett. Our emails are on the screen right now. You can also send me a quick direct message in the chat during the presentation today if you want more info. And then we set the time each semester so that the most students are able to attend, with everyone's personal conflicts. All right. And then I hope that everyone here is already a GSC member on Engage. If not, feel free to scan the QR code here or search for the graduate student community on Engage. This helps us make sure that we get invites to everyone for upcoming events. It also helps us with funding so that we can provide food at our seminars or host other fun events. So please join us on Engage if you haven't already. Also want to invite you to our LinkedIn page. You can keep up with events on there as well and see success stories and keep up with everyone. So you can search for us on LinkedIn, scan the QR code here. Past that, we also have a Facebook page. Same deal, keep up with everyone, share exciting stories, all of that. And lastly, our YouTube channel. We record all of our weekly seminars and post them to our YouTube channel within the next week, excluding a few that we didn't get permission for, but you'll be able to find this seminar and a whole bunch of other ones from past years on our YouTube channel. And then, as members of the GSC, the Dave and Susan Burt team room is available to us. We have a few nice amenities there. We have couches, whiteboard, coffee pot, microwave. So if you would like access to that, send me or Rachel an email, and we'll make sure to get you access with your student ID. And during the seminar today, we're going to have a Google form just for attendance. Rachel just shared the link right now. Please fill that out. It helps us keep track of who's attending and also helps us with funding so we can provide more events, more food, fun things for everyone. And my slide's not going forward. With that, I'd like to welcome Dr. Junke Wang, who's presenting today about advancing multifunctional heat pumps for cold climates, who is an electrical engineer in the optimization and control group at Pacific Northwest National Laboratory. So, Dr. Wang, hand it over to you, and I'll stop sharing.
Thank you, Ronnie, for the introduction and inviting me for the GSC seminars today. I will share my screen. Okay, can you guys see my screen?
1 second.
Okay. The full screen, right? No.
We see the full screen now.
Okay, cool. Yeah. Also, thank you to Professor Mitri and other GSC members for the efforts. It's a pleasure to be here. I mean, even if virtually, and reconnect with the university where I spent a few years, for a PhD and a postdoc. I'm excited to share some insights from my research journey. Over the next, I think maybe 35 or 40 minutes, I will be diving into my topic. I hope that today's topic not only provide some insight about research, but also maybe a new perspective on approaching your overall work. So looking forward to your thoughts and questions if you have during or after the talk. So I'll be happy to answer that. Okay, I think I will get started. So today my topic is about advancing multifunctional heat pump for cold climate. So this work was supported by the DOE Building Technology Office. The team members will thanks to the engineers from TRK and LG for their efforts, during our modeling process. So I will introduce our system first and show how we model the system, each component models, and how we build the controllers. Meanwhile, I will show the real experiment system, how we collect data based on a data acquisition system. So when we have model data ready, so I will show you how we calibrate and validate the model. Then, based on the model, how can we propose the new controls for control and optimization? Especially for my work is on for the supplemental space heating during extremely cold weather. Lastly, we reach some conclusions. Okay, I start with the challenges we are facing today, right? So homeowners need affordable and reliable solutions to fossil fuel-based system for space conditioning and domestic hot water. We all know, it's very hot topic for the electric heat pumps because these systems offer the most viable alternative, but their capacity and efficiency drop significantly in colder temperatures. So some manufacturers, produce like an integrated heat pump system. However, the default out-of-box control lack advanced features to maximize the flexibility and the performance. So we saw the opportunities. How can we, get innovations like advanced control and optimization designs that are able to integrate this system with thermal energy storage to provide like cost-effective, energy efficient, and greater response solutions. So here you can see this picture is a PNNL level home installed the heat pump system. So I will introduce about this. When we talk about the integrated heat pump system, an example of the system is a wearable refrigerant flow heat pump system with heat recovery. This kind of system have attract attention for potential energy conservation via heat recovery. The VRFHR system that integrates space conditioning and water heating is also called a multifunctional VRFHR system, namely MF-VRFHR. So here is an example of the residential MF-VRFHR system setup that provides space conditioning, domestic hot water, and the option of dedicated thermal energy storage. So let's talk about this system a little bit. If you look at this figure, we have the outdoor unit. I think everybody familiar with that, right? You saw a lot of this outdoor unit outside the building. This outdoor unit connects with a device via several pipes. This device we call the heat recovery unit or you call the motor change unit. I will introduce this one in details later. So basically, this device has several branches. Each branch can be connected with different indoor terminals. For example, one of the branch can be connected with the air handler unit. Another one can be connected with the hydro kit. Here, hydro kit also a device. This is a water to refrigerant heat exchanger. Can be circulate water to heat up the water tank for domestic water supply. They have other available branches can be connected with other different types of thermal energy storage systems. So after briefing this system, so what's the potential for this system? So what's the advantage? So potentially this system can utilize heat from hot water tank for space heating during extremely cold weather, because you have both space conditioning and water tank heating, right? Also, reject waste heat from air conditioning for water heating, provide free hot water in the summer. Yeah. Another benefit, we can use the hot water heat for heat pump defrosting in cold and humid conditions. But the question is, how can you achieve this potential, right? So from my work, I just focus on a system with the hot water tank as the thermal storage only. So I will study to utilize heat from hot water tank for space heating during extremely cold weather. So this is exactly the same system, but only have one hot water tank as the thermal storage. Okay, we have briefly talked about the system, but it's very important how we need to know their operation algorithm, right? So for heat pump system, you can provide heating or cooling, right? That's the normal operation models. However, for this unique MF-VRFHR system, we have a heat recovery mode we call. So heat recovery mode, basically, you have the HU operated as the evaporator. You have the outdoor unit and the hydro kit serve as the condenser. So if you look at the refrigerant flue, so you have a compressor here, produce the high temperature, high pressure liquid. This liquid will flow to one of the indoor terminals. Here is the hydro kit. Then the liquid will be condensed into the high temperature liquid. So this liquid will merge from another condensed refrigerant from outdoor unit heat exchanger. So finally, this merged refrigerant flue will flow to the heat recovery unit, then lastly back to the suction side of the compressor. So this is the refrigerant cycle for this heat recovery mode. You can see here, I also let the cooling dominant. So basically for heat recovery mode, we have two modes. One called the cooling dominant, another called the heating dominant. Basically depending on the capacity of your indoor terminals. For example, if your HU's capacity is larger than your hydro kit, that means you have the cooling dominant operation for the summer season. If you need more hot water, hydro kit has more heat produced. That means this operation will be heating dominant mode. So depending on the heating capacity of these two indoor terminals. So for other heating and cooling, that's the same refrigerant circulation, but just for different motor you have different directions. Okay, we have briefly talked about this system and talk about the operation models. So let's talk about the previous efforts on this kind of work. So we first talk about the modeling efforts previously. So basically, most of the available models is in Energy Plus. They are primarily designed for energy consumption calculation. There are few existing dynamic models in Modelica, but like water to refrigerant heat exchanger, for example, like the model for heat recovery unit. In terms of controls, usually the model cannot support motor switch and device level control. We have several operation models, right? But the available models cannot support the motor switch and the device level control. In addition, the capacity and the efficiency of these models will decline during the cold temperatures. So the objectives of this study is we try to develop dynamic models capturing transient behaviors at a time scale suitable for control design and optimization. Also, we want to demonstrate the efficiency of the developed models. Lastly, we develop some controls, to access heat from water heater for supplementary space heating. So I will start with the modeling work first. So this is a complex system, right? You have one outdoor unit, you have two indoor terminals. Also, you have a unique device heat recovery unit. So how can we model these systems? So here you can see a schematic of this system we developed in Modelica, relying on the building library and the TRL library. So here I will show you some critical components we used for the modeling. First one is a compressor. You can see here compressor. This is an efficiency model that the efficiency-based model that accounts for rotation speed, three efficiency, and displacement. Yeah, by the way, I'm not sure if any of you have taken the heat pump class. So basically, if you familiar with the heat pump, so there have, when you model it, you need to know the speed, like the three efficiency, such as the isotropic efficiency, volumetric efficiency, and effective volumetric efficiency. So that's the critical parameters, considering to build the model. Next one, I'll talk about the hardware tank. You can see here, hardware tank model is a single internal heat exchanger representing the heat transfer between this hardware tank and another hydro kit. So we said this hydro kit is a water to refrigerant heat exchanger. So the water can be circulated between hydro kit and the hardware tank to heat up the tank when you have domestic hot water requirement. Meanwhile, the model is able to capture the thermal stratification within the tank. So that's very important features, because usually you will withdraw water at the upper layer of the tank, but you have city water in at the bottom of the water tank. So also there are other configurations, but this is usually the typical configuration for the residential hot water tank. The third one is the building model. In the building model, this is a reduced order physics-based model. So this model considers like walls, roof, floor. Meanwhile, this model is integrated with the air handler unit. You can see here air handling unit. So they have integration in each other. So next one, I will introduce the unique device heat recovery unit. So this unit, I said, is a unique device because there are no available model available for this device. So we build a new model for this heat recovery unit. Lastly, I will talk. Sorry. Yeah, this heat recovery unit is not available in current library. So we created a new HRU model for this system. So this is how we model this entire MF-VRFHR system in Modelica. So later I will show you how where the resources you can rely on if you want to build this kind of system. So here I list a table to show you the paths for each library you can refer. So here I want to emphasize still the unique device called heat recovery unit. If you look at this right side two figures, the right figure shows the physical schematic of the HRU. Right side is the model schematic of the HRU in Modelica. If you look at this heat recovery unit, basically this unit uses switching valves and a heat exchanger to direct refrigerant flow for heating or cooling, enabling heat transfer between branches like HU and hydrocide, and facilitating heat recovery. So what's the inside, inside the HRU? If you look at this one, we have several different types of valves. For example, valve A, this is a suction or called hard gas solenoid valve. This one will be open, to the indoor unit, either to the HU to the hydrocide, based on you have heating or cooling demand. Another type of valve is valve B. It's a hard suction. Sorry, this valve is an electronic expansion valve or EEV. This valve utilizes a PI control to regulate the subcooling. Basically, that's the subcooling between different refrigerant pipes. We also have other different types of valves, but we ignored during the modeling since there are negligible impact on the heat transfer performance. So this is the unique device we have introduced, So next one, I will start with how we build controllers, for this system. Control is very important, right? Even you have the model, if you do not have control, you cannot operate the model for different operation models. So following the same way, I will just introduce some critical controllers we use. For example, first one is the system controller. This controller defines the dominant heat pump motor and the individual indoor unit motors. Like here in the Modelica. Then other is the component controller. For example, for here, this component controller will receive operation motor decision from the main controller, then modulate the system components such as EEVs, compressor, and fans. So EEV, this valve, is controlled by a PI controller, modeling the openings based on either superheat or subcooling set point. For VRF system, we have a lot of EEVs, like you have HU EEVs, you have Hydra EEV, you also have ODU EEVs. So this is a very complicated system. So that's why you need to have a lot of EEVs. For compressor, we still use a PI controller to track the suction or discharge pressure set point. We also have fans like indoor fans, outdoor fans. So this fan is to modulate the speed based on the temperature set point. Another two components is HRU and the pump. Those are controlled by on-off controllers. So they will receive the operation motor signal from the main controller based on different operation motors. So this is how we control this entire system. When we have a model controller ready, next step I will show how our experiment system in a real building, how we collect the data. So from this figure, you can see we have two identical PNNL level homes. So this home is a single family residential homes in Richland, Washington State. We also have the MF-VRFHR system installed in one of the level home. So this system has a 4-ton outdoor unit. 4-ton outdoor unit like this picture. We have 2.5-ton for the indoor HU. We also have a 2-ton for the hydrocide. You see here, this hydrocide is connected with the hot water tank. The tank has 80 gallons or 300 liter. So I also have a data acquisition system. We are able to collect the temperature, like flow rate, the power consumption. So here just one example how we plot the data. So when we have the model and the controller, we already have the data real experiment system, right? Then what's the next step? We need to calibrate and validate the model, right? Make sure this model is stable and robustness for different seasons, right? So next I will introduce how we calibrate these models. So we adopt a genetic algorithm to calibrate like some critical components. For example, compressor and hardware tank. For hardware tank, we adopted a 3-step calibration. So why we adopt 3-step calibration? Because hardware tank has different layers. That have thermal stratification. If you want to identify the tank model correctly, you need to consider the features. So that's why we adopt the 3-step calibration. So step 1, we did not consider water draw from the tank. Meanwhile, we did not consider the water circulation between the hydrocide and the hardware tank. So in this case, we are able to calibrate the tank insulation model, such as the parameters for thermal conductivity of tank wall materials, tank cylinder overall heat transfer coefficients. For step 2, we consider water withdrawal but do not consider water circulation from hydrocide. So in this step, we can calibrate the tank discretized heat balance model. So the calibrated parameters include the tank to heat exchanger heat transfer efficiency, the tuber side heat transfer coefficient. Last step is we do not consider water withdrawal, but we consider water circulation from hydrocide. So this step, we can calibrate the buoyancy and the internal heat exchanger model. So the calibrated parameters include internal heat exchanger parameters, buoyancy effect parameters. So after the calibration, you can see here is the results I plot here. The left figure show the calibration for compressor. By the way, for compressor calibration, because we have the manufacturer data, this is actually enough. So we use the manufacturer data to do the calibration. If you look at the x-axis, we have rated power. Y-axis is the predicted power. So it's pretty, actually, we have the R-square value more than 19%, more than 0.9. So meanwhile, if you look at these 3 figures, that's the different days in June and July. The x-axis is the measured tank temperature. The y-axis is the simulated tank temperature. So you can see the calibration works. The measured temperature have very good fit with the simulated temperature. So that means we have calibrated the critical components. So next part, I will show how we do the validation for different operation models. So when you have calibrated the component and models, then we need to do the validation. Make sure the entire system still work robustness for different operation models. Here we have 3 operation models. Like I mentioned, we have heating mode, cooling mode, and another is heating recovery mode. So here we use the evaluation index of CVRMSE and AMB to evaluate the accuracy of the model. Overall, you can see this accuracy is less than 15%. That's the criteria defined by Accuracy Guidelines 14. We have actually all this accuracy values is less than 15%. Also here I list some variables, parameters we calibrate. We plot here to show how the measured one compared to the simulated one, because these parameters are critical in the system performance, such as the Swiss air temperature, related to the occupant thermal comfort, right? Also have compressor speed, other unit power, these related to your energy consumption. Last is hardware tank temperature, because you want to guarantee your tank temperature can reach the requirement, right? If there have people using hot water tank, for shower or for hot water use, right? So overall, you can see the measured one match with the simulated one with very good accuracy. So if you have any questions, feel free to stop me, or if you think I talk too fast. So I have the last part of my presentation about the controls. So we have the model is ready, we have calibrated model, right? How can we control the system to achieve the objective like I mentioned? How can we still maintain our space temperature, air temperature during very cold weather conditions? So basically, we are trying to coordinate the domestic hot water control that minimize heat pump operation during the coldest hour of the day. Typically, at the early morning, like maybe 5 or 6 a.m., when efficiency is lower. So basically, you will start with you discharge your tank first when the outdoor temperature is very cold. Then you charge back your tank when the outdoor temperature is hottest during the day. But the issue is, since our system, you also need to use the hot water, right? You need to guarantee when you discharge or charging your tank, there are no water withdrawal. Meanwhile, during your discharge and charging period, there also need to no withdrawal. Otherwise, you cannot guarantee your hot water tank temperature. So that's why we build a flowchart to show the control process. First, we will identify the coldest and hottest periods during the day for discharging and charging. So then we will check if there are any withdrawal for discharge and charge period. If the answer is no, we will calculate the sum of outdoor temperature for all possible intervals. Then this part you will be able to check if you have a uniform hot or cold days or not, or the periods which is not enough, for the discharging process. So if all these processes no, we will list all the possible periods without the overlap. Then to do another check, do you have water usage between this charging and discharge period? If the answer is no, then we will set up the discharging and charge period. Then generate your operation motor signal to control the system operation. But if all the answer is yes, so we will skip this day and generate the constant control operations for different valves. So for this control logic, compared to the out-of-box control from the system, we propose two new controls. The first one is we added a new EV within the HRU. This EV will be controlled by a PI controller based on the compressor suction pressure and operation motor. So why we do this control? Because for this particular heat recovery mode, we want to guarantee you're still able to get enough low suction pressure, so the outdoor unit still can able to absorb enough heat during the cold weather conditions. The second thing is instead of regular controller, for example, air to refrigerant heat exchanger, usually you control the EV using a super heat set point like 5 to 10 C, right? But for this particular scenario, we have the water to refrigerant heat exchanger. So this EV is adjusted via PI controller, but we maintain a higher super heat set point. For example, we use 40 C. So in this case, you are able to absorb the heat from the tank. So based on this new control, we investigate a total 21 scenarios. We consider 3 withdrawal profiles and 7 outdoor temperature profiles. So here I can see the 3 water drop profile. Basically, we consider high water usage, medium water usage, and the lower water usage. These 3 water usage profiles from the ASHRAE standards. These 7 outdoor temperature profiles also from the Alaska. You know, they have a lot of cold outdoor temperatures during the winter. So if you look at this sub-box plot, we compare the baseline with our new controls. So for the temperature, we have the set point at 21. So here show the HU heating transfer rate increase for the new control. So overall, we got the average improved HU capacity like 7%. So the zone air temperature can be improved around 1 Celsius, but we negative impact energy consumption. So that's the trade-off, right? You want to get more, you want to increase your space air temperature during the cold period, but there are a balance of later you still need to charge back the tank. So that's why you consume more energy than the baseline, but the total consumption is less than 4% compared to the baseline. So here we want to further investigate the benefit if you have a larger tank size, because you want to use the the heat stored in the tank, right? Ideally, if you have a larger tank, that means the tank can provide enough heat, for to discharging process. So here we compare the default tank, that's the 300 liter, and the double size tank. So let's look at the left side figure. This both figure has the same plot. So the first one is the space air temperature. We have the 24 hours from 0 to 24. The second figure is the HU heat transfer rate. The third figure is the motor switch signal. I will introduce one later. Then the fourth one is the tank temperature. Last one is the outdoor temperature. Here is an example. You can see the outdoor temperature here is very cold. During the early morning, it's less than -20 Celsius. So if you look at the curves, the red curve is our new control. The blue curve is the baseline. You can see during the cold period, our new control is able to maintain the space temperature at a set point. Meanwhile, you can see the second figure, the HU heat transfer rate is increased during this period. So because we withdraw heat from the tank, right? You can see the tank temperature has dropped. So basically, we will switch the operation from heating to cooling here. Then we will keep the off operation until the outdoor temperature is the hottest. We switch back to heating. So that's when you switch back to heating, you can see the tank temperature will increase, right, to reach the tank temperature set point. However, you see the issue, right? When we switch back to heating, the space temperature cannot maintain anymore during this like around half-hour period. So that's why we further increase the tank size to see how about a double size tank perform. So you look at, we still keep the same discharge period, like around 3 hours during the early morning. But you can see the space temperature can still maintain at the set point, but we avoid the deep drop when we switch back to heating when the outdoor temperature is hottest one. Meanwhile, if you look at the tank temperature, here the lowest temperature is around like 30, but for this baseline tank, you can see it's almost less than 20 C. So what does that mean? That means because your tank size is large, right? Your tank can still provide enough heating for discharging process. Since the tank temperature did not drop too much, that means when you're charging back the tank, you will spend less time. Meanwhile, you have less impact on the space temperature. So that's the finding we find through this process. You are able to maintain we are able to minimize the significant drop in the surface temperature when we switch back to the heating mode. We are also able to reduce the tank temperature decline for extended discharge hours and improve the tank temperature recovery. So here is the table, basically all the results from the figure. You can see it's around like 1 Celsius improvement during the switch period. If you consider the full period, 24 hours, we have the total energy consumption is less than 7%. So that's the trade-off. I mentioned you want to improve your actual heat transfer rate, then you need to consume more energy, but this consumption is less than 7%. Okay, that's all my research work. Here's some conclusion we made. So we developed and validated the residential MF-VRFHR system. We are able to calibrate and validate the model. So we demonstrate the efficiencies based on different operation models. So lastly, I also show you how we build the new controls to maintain the space air temperature during very cold weather by accessing heat from hot water tank. So for future work, we are trying to investigate different tank configuration. Like I mentioned here, we only have one tank, right? Also in the tank, we only have one single heat exchanger. For example, if we have 2 heat exchangers, or if the heat exchanger is not using water to heat up, instead of you use refrigerant direct to heat up the water. So for the control part, we will try to implement and test the new controls in our real test bed, like the system installed in the lab home. Here is some papers we published for this work. Okay, thank you very much for your attention.
Great. Thank you, Junke, for your presentation here. It was really nice.
Thank you. Yeah, it's okay. It's in 40 minutes. I think it's good, not beyond the time.
Yeah, perfect timing. Right. So now I'd like to open up the floor for any questions. Let's see, Andrew, you have a
Andrew, hi.
Yeah.
Hello.
Hi, Andrew.
Oh, sorry. Yeah, sorry. Hi, Dr. Junke. Nice to see you, and thank you so much for the presentation. Was very interesting, and the work was quite impressive that you guys are doing. One question I wanted to confirm is the outdoor units and the indoor units, like those the coils, the heat exchangers. How did you guys parameterize? Like, how did you set the parameters for those?
Yeah, that's a good question, because when you want to do this, a Modelica model, Modelica models most are physics-based model. You need to know the specific configuration for each component. So for example, like the heat exchangers you mentioned for the outdoor unit heat exchanger or indoor unit heat exchangers, we are trying to get as many as possible the data from the manufacturer to see like the fin diameter, the configuration, all the parameters. If some parameters you did not have that, we do some open loop calibration. Basically, we set off a range of the parameters using a genetic algorithm to find the best fit of the parameter values to achieve the performance curve, like we draw from the manufacturer. Under different conditions, basically under different conditions, you will got a different capacity. So that's I think that's the tricky part, for this physics-based Modelica models.
Oh, that's nice. For your validation, did you guys have like longer results? I saw that you just had maybe like a few hours. Did you try to look at how the measured and simulated data compares if you kind of go from cycle to cycle?
Mm-hmm. Yeah, that's a very good point. Because in our system, this system is the compressor in the real system is compressor controlled by on-off control. However, in our model, the model still use the PI controller because it's hard to model the on-off control for the compressor. So we are trying to able to abstract the period. For example, here I marked a few hours. We got the continuous operation data. That means the compressor continue operation, your indoor and other units is continue operated. So that's why here you see we only validate a few hours for different days instead of like an entire day or a week. So that's some shortcomings for this kind of system. That's better if we can build maybe an off control for the compressor. I think you asked this one before we talked, right?
Yeah, yeah. Thank you so much.
Yeah, thank you.
Cool. Are there any other questions?
I'd like to make a comment.
Yeah, sure.
What you're focused on here, Junke, and I suspect it's the same with Lee, is you're looking at a cyber-physical model and controlling the cyber-physical model. Okay, cyber-physical system. I have two questions. One, from the cyber-physical side, do you see a universal controller being developed? That means now we have a huge number of sensors. I mean, and they're dirt cheap. And so the question that comes up is that we have different applications. Can we use large language models to come along and say, these are the sensors that you need that exist in the world, and this is how you can configure the system to make it happen? Do you think this is worth investigating? That's my first question. Go ahead.
Yeah, I think I think you asked this kind of question. I mean, even during my PhD. Yeah, I think that's a very good question. If we can find some universal control, for different type of system, but in real now in practice, for each specific system, we need to build the specific controller to achieve the purpose you want. But if you have the similar system, for example, the very mature controllers, for example, like on-off control or PI control, for the EEV or fan pump, this one I think is universal. You can use for different type of systems, but the question is how you adjust their set point to track the variable you want. So I think that's the, but this also that's a very easy controller, right? Like PID, PI control, off control. If we want to build a complete control, currently I don't think there have any like a universal controller that will be suitable for different mechanical systems.
Models.
Yeah.
And let's say the large language model is a database of all the controllers that we can have in the world, all the different types. Okay? Then if a designer goes to the large language model with all this information and says, I want the initial configuration for X or Y or Z, the large language model could come up and say, guess what? This is where you can start. Then, of course, you can adjust whatever you want to adjust. As you talk to it, you say, I want this, I want that, I want the other thing. But it's a total different way of designing a control system. And in this thing, you could have virtual sensors, you could have physical sensors, you could have all sorts of stuff, all range of sensors, because what you're really looking at is the concept of a large language model populated with all this information.
Yeah,
Yeah,
I think yeah, that's a great concept. Just want to add in one of my input is even though we have so many sensors collect large amount of data, I think for dynamic system control, the real issue is you have always data training process, learning process, and then in the reality, it can go beyond the range of the data set. So once you first time going beyond the range, and that always creates challenges to have good response for the system that you were not trained for the operation you are running into. I think that some challenges need to be addressed before we can think about the universal system.
But that's what you've talked about, Lee, is a software issue. So you could
It's not
have
software
software with
issue.
different modules that go along and say, okay, I want this controller or that controller from the software side.
It's not
Because what you're
software.
looking at is a cyber physical system. The cyber is the software that deals with it. And I agree with you that you need algorithms that are responsive and in time and all this sort of stuff. But my question is that since we have this large language model, we can configure the basic system, and then using ChatGPT, we could come up with the algorithms, because ChatGPT does it very well, to tune the algorithms to do what you want. So this, I think, is a frontier issue. This is not something that we'll do tomorrow, but I see this as a possibility.
But once you become system domain free, because you simply don't use this physics-based laws in your controlling, right? So when you have large amount of data, you indeed don't need the physical laws to capture the system behavior, so you can do a good control. So what I'm saying is, if this data beyond the range, what we use currently, because we know system behavior is based on physical laws, so we can predict how system going to respond when you go beyond that data range. But if you go beyond the system domain, you don't have that prior knowledge about the physical laws. It's just harder. I don't see it's not possible to have.
You're talking about two totally different things. You're talking about how you operate and maintain and do that stuff. I'm talking initially about how you come up with the design. That's a totally different story. So
I think this is part of design.
I think you can call this co-design. Actually, my colleagues, we also doing a similar work. So we did not use like ChatGPT. We just based on the design and control part, we merge them together. For example, at the beginning, when you design the system, for example, for the HU side, for the tank side, we already design based on the optimal one. Instead of you already have existing system, you are trying to build an optimization algorithm to optimize the operation. So this part they are just called the co-design work. Yeah, I think that's a very good point when you talk about the large language model, because now at PNNL, I heard a lot of teams, they are also doing the work like you mentioned. They are trying to feed the model a lot of the data, to see if the model can create some innovative, solution or either control or design to work with the research they did. For example, for the grid edge project, I knew some of the colleagues there just use a lot of data generated to the model. This is purely just like a black box model, right? You don't know anything inside. You just know their input data and then show the output to see if it makes sense or not.
Okay, so that's my commentary. We got a discussion.
Yeah,
he has a different view, which is fine. Go ahead, Andrew. Sorry.
Yeah. Can you hear me?
Yes.
Well, I wanted to also ask one question that is kind of similar to the conversation you guys were having. How did you initialize the different components in the model?
How to initialize different? Oh, you mean how we set up the initial parameters for different components?
Yeah, for like the evaporator, condenser, the initial.
Oh, okay. Yeah, this one, just based on experience, you give the initial value. But I want to say, no matter which initial parameter you set, you put, maybe it impact a little bit in the beginning, but after a few, I'm not sure. Maybe from our experience, after like around 10 minutes, it's already reach the values based on the law. It will not impact too much for the initial parameters.
Okay.
Yeah, if you saw something wrong, I don't think it's caused by the initial parameter for the component. Maybe, you know, if you did not give a reasonable initial values, maybe the model will fail, you know, at the beginning. If the model can run across a few minutes, it should be, if somewhere the model stopped or failed, it should not be caused by the initial values.
Yeah. Okay.
Cool. I have a couple questions. Well, I had a whole bunch of questions, but I narrowed it down to my favorite two.
Yeah, sure, go ahead.
So I was wondering, what's the acceptable temperature range for your water heater, or for the water in the hot water tank? And how hot can you make it using the heat pump?
Yeah, I think that's a good question, because usually if you go hotter, you can store more heat, right, in the tank. Later you can discharge. But because, you know, we in our study we are trying to investigate the tank, you know, for the default set. So we still maintain the tank temperature at like 50 C with the 2 Celsius dead band. But for my another project, the heat pump, water to water heat pump plant, actually we set up the water tank temperature at 70 C, you know, try to
Wow.
storage of as much as, you know, you can. But the thing is, you cannot go beyond too much, otherwise the water will be boiling, right?
Right.
So that's, yeah. Also, you have the temperature is hot. That means you have easy to lose heat, you know, from the surrounding.
Yeah, that makes sense. Okay. And then my other quick question was, have you done anything where you had like a separate tank that wasn't for domestic hot water where people are using it, but done like latent heat storage?
Yeah, that's the work I will try to next say. But one of my colleague investigate the parallel two tanks. We still use the water, not the, like you mentioned, the one for domestic hot water, one solely used for the storage, right? So we did not do this case. We have two tanks parallelly. Both tank still has the hot water withdrawal, you know, based on the demand. But sometimes maybe one tank has a less water withdrawal, maybe one have a higher. So overall, we find that the energy saving, I mean, the energy consumption is not energy consumption compared with the baseline. You know, we see a little bit saving, you know, compared with the baseline.
But
Yeah,
not enough to justify the cost.
yeah, but not enough. Yeah. So I think that the issue we still have is how we can, you know, to better control this system, because this, when you have another tank, you know, it's very complicated. That means you have 3 parallel terminals. So how that case you can run, for example, run your HU in cooling, one tank in heating, another tank maybe even in cooling, you know. You depend on the operation mode. So this is very complicated, you know, operation mode. Even currently we have this two like either heating or cooling. We find that this one also is already very complicated. I spent a few months to get a solution. How can we able to withdraw heat from the tank? Because for the baseline control, like the outbox control, this system did not have this ability. This system only can run either heating or cooling, or HU in cooling, tank in heating. That's only 3 models. Because now we want to run the tank in cooling, right? So you are able to draw the heat hot water from the tank.
Okay, cool. Thanks. Okay. Dr. Song, I saw you unmuted a couple minutes ago. Did you have a question?
Yeah, actually I wanted to ask a follow-up Andrew's question, but it's okay. I think we ran out of time already. I can ask later. Yeah.
Okay. we are approaching our time limit here, so if anyone has any last minute questions, feel free to speak up. Or sorry, I just want to add on, Junke also shared his contact information if we can't get to it. But I see Naran, you have a question.
Yeah, thank you, Junke, for the presentation. It was actually very detailed and wonderful. I just want to ask like a very short question regarding how you calibrated like those components. So I saw that you use like a GA, which is genetic algorithm. So like what was the logic behind using genetic algorithm for like a dynamic system, like for like your compressor or hot water tank?
Yeah, we build an object function. You are trying to minimize the difference, between your measure and the data you collected. So basically, for genetic algorithm, there are no absolute optimal value solutions, right? So you have a list good fit list of the values for each value. Then the genetic will do the search based on the object function to find which set of parameters show the best result.
So you use the measure data or use the manufacturer?
For the compressor calibration, we use the manufacturer data, but for the tank calibration, we use the real data from the system.
Yeah, but that's again, see, when you do simulation, you had a negative 20 degrees Celsius operation, right? But when you collect the tank operation or the compressor operation data, do you have anything go that extreme?
Yeah, that's true. Even in Richland, the lowest temperature is like maybe -10 or -5. We did not have the larger range, from -25 or to even 240, right? So
Yeah.
that's the maybe errors accumulate if your model did not well calibrate or well validate, since operation range can be very large. But when you validate, you just select a range of that.
Yeah, I think that might add in some challenges you had with the extreme cold condition controls. I don't know, it can be a factor.
Yeah. I think that's I think that for the compressor it should be okay, because we do the open loop validation for the compressor model. This compressor conformance can be even 20% until 100%. This should be okay, capture the behavior. The issue is for the other part, like your tank, your HU, because this one HU also integrated with the building. So maybe the building load, have a bigger dynamic, you have a large load variation. Instead of the period we do the calibration and validation.
Yeah. Okay.
Well, I think we're at our time limit now, so I want to say again, thank you very much, Junke, for the presentation. And if anyone has any further questions, again, you can reach out to Junke, Dr. Wang. You can also send me an email or chat, and I can help you get in touch if needed. And thanks everyone for coming to our seminar this week.
Thank you.
Thank you, Ronnie. Thank you, Jesse, man. Yeah, good to see you guys.
Thank you.
Thank you.
Have a good day. Bye.